any sort of physics analysis, okay, if you're doing any sort of physics analyses, you'll probably have to touch this at some point, or at least it'll be sort of under the hood and making something that you'll be using. If you're working on like more sort of detectory stuff, like I don't know, installation, integration, you might not need to use it, but it's if you do want to do any physics analyses, it's pretty useful to know. Okay, so we're going to be focusing on using root for relatively simple tasks today. And there will be an exercise on building slightly more complex software. Really, it's just compiling a couple small programs. Okay. So first off, what is root? It's a big software framework that provides lots of tools for physics analyses, including data persistency and input and output, data visualization. Let me get this out of the way. Is there a little mic here? I see. Okay, there we go. Okay, so data persistency and I/O, data visualization and analysis. So you can do something like look at some distribution and try to fit something to it and say, okay, this doesn't really fit well. Maybe there's something going on. There's a big C++ library for physics software development. There's an interpreter and a compiler, so you can make small little macros or scripts, I should say. And there's also a Python interface if you want to do that. And I'll touch on both of these. I'll touch on the second one later today, but in here I'll talk a lot about the interpreter and the compiler. Okay, so I guess by show of hands, how many people know C++ or have used it at all? Ish? Okay, okay. So root can actually kind of be a good way to sort of explore and learn how to use C++. Some things might require a little more technical knowledge, but maybe throwing yourself in at the deep end is kind of a good thing sometimes. That was a bit of a joke. But anyways, let's just move forward. So root comes with a prompt, so this opens up the root environment and allows you to do things in C++ basically. And it's compiled just in time, so or rather, in here it's just interpreted. I guess later it's compiled just in time. Oh, those are the same thing. Anyways, you can work interactively using C++, and there's some helpful root commands, and you can see all these if you just type -help. One of the most important ones are these two, which is .ls, which just lists the root objects that are available in memory at the time you can access, and .q when root crashes, and .qqqqqqq if root doesn't quit after that. So I include this just to say that even whatever ChatGPT or Claude or whatever can say, yeah, this is relatively important to know. And within root, when you open up the root prompt, the C++ standard library is available. So you can do things like open it up and say, hello world, and start to use C++ types. Yeah, I guess I should say, first off, the way that you open up the root prompt is just by typing root. And it then puts you in the root environment. You can start to do things like this. I have a tip here. If you don't want to have this big splash screen every time, you can just type root-l. So that's good to put an alias if you know what those are for Unix. Okay, and you can do a lot in the prompt. You can instantiate more complex types than just these integers and doubles. So you can make some map of some crazy key and value relationship. And you can use it to do memory management and define functions and call those functions. Basically, you can do C++ in it. So there's, so moving on from there, there's an important concept, and we'll go into this more deeply later, called T-files. These are the sort of persistent objects within root. And those root and C++ objects can be stored within T-files that you can then read out later. And you can open these simply with the prompt by just typing root and then the name of the file that you're interested in. And you can see their contents. So the root objects, which are always called T something, can be accessed directly by their name. So I open up the file, and then I type .ls, and it shows a few different things in here. It shows a th1d and a named myHist and a ttree named myTree, as well as just a standard vector that I've called myVector. So this first one is a C++ object, but these two are root objects and indicated by the fact that their first letter is T something. Yeah, and you can access them just by their name right out right out the box. So if you type myhist, it shows some th1d pointer and their location in memory. Same thing for the tree. And you can also call their methods just by accessing like pointers, like normal. So you want to be, if you do come across a file and it has a bare C++ object in it, which is not often, but sometimes it happens, you need to use root's IO layer. So you sort of have to pipe it into a, you have to use this method called get. Do I say that? Yeah, okay. So you open up the file, it's actually stored in memory as underscore file 0, and then you have to use get on that pointer and the name of that object, in this case my vector, and it returns a T object, which is sort of the generic root IO layer that it uses for basically everything that can be stored to a T file. And if you want to actually do anything with it, you have to cast it to the correct pointer or the correct type. And then you can start to access the data from it. So you could say, get the vector, store it as some, actually store it as a pointer. And then you can dereference it, and then you can start to see what's inside of it and look at its size and whatnot. I make a note here that so this is sort of an indication of why you need to use this sort of T-object layer, is because root doesn't know how to handle that right out of the box, so it will give you a segfault. This will be really common in root. Like, that's kind of just one downside of root, is sometimes its memory management is a bit wacky, and you'll start to get lots of these segmentation violations, and sometimes you can't quit out of it, which is why the QQQ is really necessary. Anyways, so this is a bit cheeky, but yeah, get used to seeing that. Okay, right, so you can also access those root objects with that same IO layer. So this is a general recipe when you're building more complex programs, especially in C++. You want to, you can pipe one of these, for example, this histogram that I looked at earlier just by typing its name. You can also use that get method on it and put it into a pointer of the correct type after you cast it. Okay. And this is the sort of general recipe. Yeah, if you want to do something that's actually compiled later, this is more or less what you'll have to do. Okay. So you can do a lot with the prompt, but it only gets you so far. And so you could do, and you might want to look at some things in a T browser or visually. So you can make an instance of T browser within the prompt. It doesn't matter what you call it. It's just whatever your hands like to do by muscle memory. Some people even just do T browser, and it gets you the same thing. So it just instantiates a T browser in memory, and then it opens up this GUI that you can then work with. If you're working on remote computers, this might, well, if you're working on the Jupyter Hub for this won't work. If you're working on GPVMs, these are the sort of general use machines that we use for Dune. If you have to SSH into something, you have to do something special to make sure that that visualization actually gets to your computer, or else it's really slow. So beware when you do this. It's nice on your own laptop, and if you set up other things correctly, I won't talk about that. So, just beware. But it can be really nice to work with these. So you can open up that file just like I did previously. Open up that file, start a T browser. This will pop up, and then we can start to look into the contents of that file. Right now, it's pretty simple. It's just a few objects: the vector, that histogram, and that T tree, stored at the top of the file. I'll describe a more complicated layout later. But yeah, if you just double-click that, it'll show these. And then you can start to double-click on other objects, and we'll start to visualize those within what's called the T canvas. I don't really touch on that here. This is essentially just the object that root uses to draw things onto and then visualize to you. I don't have any more about this, but you can do other things. These T canvases are actually interactive. You can, for example, click on the axis. You can zoom in onto specific parts that you want. And you can right-click, and there's a object box that'll pop down, or an option box, and you can change how the things look. Anyways, there's lots of how to learn root is just explore, look at the reference pages and whatnot. So I don't go into this specifically here, but anyways, I'll leave a little breadcrumb for you to follow. Okay. So now, I talked about using the prompt and sort of looking at things in the GUI, and that only gets you so far, so let's talk about macros. So you can write little scripts, and Root refers to these as macros, to save that code and share with others, and to sort of reproduce what you've been doing, so you don't have to do it write the same commands over and over again within the prompt. So the macro structure, is pretty specific. If you make a file with the name test macro in this case, you have to have a function within that file that matches that name. And that's how Root knows which function to actually call when it's operating. So in C++, you might be familiar, you'll have to, when you make a C++ program, you'll have to include a main function. That's essentially what this is. You have to have the name of the file match this function, and that's actually what gets called. And what that actually allows you to do is have other functions that you can then reference within the macro itself. Okay. So you make a file, and you make a function that matches the name up to, I guess, the appendix. And then you can choose whatever return type. It doesn't have to be void. It could be int. It could be whatever. And you can also have arguments that I show here. So what this one does should make a Gaussian distribution with a mean of 1 and a width of 1. And do I actually go through? Yeah. So what it does is, by default, it makes a Gaussian with central value of 1 and width of 1. I provide it with some arguments. I start some random number generator. I make a new output file called a T file. And I tell it to overwrite any previous one. I make some histogram for output. And then I fill it with some random numbers in a loop here. And then I write it to my file, and then I close that file. I'll go into sort of how this works more in depth later, but this is just sort of to give you a functional idea of how this would work. Make a quick note here that lots of things in Root take C-style strings, not C++ standard strings, so this is necessary. Just take note of that for later. Anyway, so yes.
So during the week, the student learned that in C++, most of the cases you have a main function.
Yeah.
Is there any reason why you don't need the main function here? Or
why you don't need a main function?
Yeah.
Yeah, so the main reason why you don't need a main function is because... Yeah, right, like it's a... Sorry, what did you say?
Yeah, so early in the week we learned from C++,
yeah,
that C++ use always a main function.
Yeah.
So in this case, your macro is just the function that you're going to run. Right?
Yeah, exactly.
So can you elaborate a little bit why you don't need to have the main function when you're using these macros?
Yeah, so I guess that's...
Not mandatory.
Yeah, I guess that's because you're not compiling it in full, so you're using Root's internal interpreter to look for the specific function that matches your macro name, and then it calls that, rather than setting up an entire program, like a process, that then does things within it. So that's my best guess. Yeah, right. Yeah, that's a better way to put it. Right. Root is root instantiates some main function, and then you pass it the macro name, and yeah, that's what it calls. That makes sense. Okay. So there's actually several sort of jumping off from that. There's several ways to actually run this macro. You can run it from your system command line by just providing it to root like this, and you can see it opens up the prompt, and then it says, okay, I'm processing this macro. This is some output that I've written, and you can tell it's running that way. You could also load. You can also start the prompt, and while you're in there, load it and execute it in one shot. That's what this one does, so by dot lowercase x. And then you can also do it, load, and then execute. So it split this up into its two parts with dot capital L. And then you load up that file, and then you call it with, you call that function. You can provide it with arguments if you want. And I just had default arguments, so that's why nothing is here. There's a question in the audience?
Yeah, I want to ask real quick. So I worked with Root a little bit, and every time I put it into interpret mode, it crashes basically. But if it goes in compile mode, it's just fine.
Yeah.
And it's like, what is like the
I don't know if it's a machine problem, but it might just be like there might just be some small weird little bug within your code that the interpreter doesn't know how to handle. That's my best guess. I'm not sure. It could be something wrong with your installation as well. If it's trying to load up a specific library and it can't, it should tell you that it's not doing that. I don't know, but yeah, we could maybe during a break maybe you can show me what if you have that. I can take a look at it later. Yeah. Okay. Right, so this is how you would run this, and this kind of shows what this looks like. I've generated some random numbers, and it's centered at 1, and it looks about a width of 1, and you can see there's some text here that shows that's about right. Okay, you can also provide arguments if you have them for your macro, and you can do that in any of these 3 styles. From the system command line, you can provide it just like this. You need to wrap it around with single quotes to indicate that this is a string, because the parentheses mean something in Bash and other shell languages. And then calling them within the actual prompt itself is pretty self-explanatory. You just give it some parentheses and you give it the arguments that you want to provide. And you can see, I've changed the distributions that I've created accordingly. Okay, so that's using them just by compiling just in time, but you can also compile them and then run them multiple times. And this helps you check for bugs and helps improve performance as well. To do that, you just add a plus sign in any of those commands. So whether that's on the system command line or in any of those 3, you can just add that plus sign, and then it will compile it and then run it. And then you'll have that on your, you'll actually have a shared object that you can then run within root. And you can see that a bunch of errors pop up, and this is just missing includes, but it shows that it's actually trying to compile it. It doesn't know where to look for certain things like what standard out, or cout and endl and th1dr. And so it says, fix this before I can actually finish compiling. Okay. So I just add those and then try it again, and those go away. So that's kind of what we'll be moving to within working with C++, and with root is just try to compile. Something's wrong, it tells you what it is, try to fix it, and then you fix it, and then it works. Okay. So yeah, so the example here, I say just include the correct headers, and those errors go away. And a quick sort of tip is that root headers are usually just t and then the object name .h. And within macros, you don't have to do anything special with telling where the includes are. You can just do these at the top of your file, and it should be all good. I'll show you later how you can actually do this when you're compiling as well. Compiling like with G++ or Clang or whatever. Okay, so now I'm going to talk about common root classes. I just want to check the time. The clock, okay. Okay, so before I do that, are there any questions up to this point? Or any further questions that you have? No? Okay. Okay. So this next section we'll talk about some of the most common root classes that you'll encounter. For storage, there's tfile and tdirectory. I've already shown you tfile. For histograms, there's th1, 2, and 3. There's something called graphs, and there are several types of those. And then there are n-tuples. Okay, I don't actually get to t-chain, my apologies. But t-tree is sort of the most ubiquitous one, at least for the time being. Now, whenever you're working with root objects, what's nice is that you could just, use your favorite search engine and ask, root, the object, and then class reference, and it should pop up. And the root documentation is pretty good, so whenever you start to delve deeper into root, this is I highly recommend using this to find out more about the classes that you'll be using. Okay, so for storage, we have tfile and tdirectory. So root files, which is the tfile, are organized themselves like little file systems, and they can hold multiple t directories, and or T objects, and those directories can themselves hold more T directories and T objects. So it's kind of nested just like a normal file system. Right. So here in this example, I've made a new file. I just call it tfile with directories.root. And I've added some nested directories. So that the T file, I've just, from the top of the T file, I've made one directory cut, just called it dir A. And then under that directory, I've made two new directories called dir A1 and dir A2. You can see that by using, you can see that when you type .ls, and you can see the sort of structure here, but maybe if you prefer to look at that visually, you can open up a T browser like I showed earlier, and click on these directories, or the file and then the directory to expand it, and you can see the structure that it created there. I make a note here that I happen to call the pointer, the actual pointer that I give, or that I have within the root prompt, the same as the name of the T directory, but that's not necessary. So you can be a little flexible with what you name things, just so you know. Okay, so I use this, just to point out, I use the make dir, or the mkdir command, which is similar to Unix and Windows, to create those directories under the T file and the directories themselves. So it's pretty transparent or self-explanatory. It acts like the file system that you're used to. You can also use cd to move around the file as well. So I can, after I make those directories, and I've stored them in a pointer that I want to reference later, I can call cd on it, and then I move into that directory, and then I can then see what's under it. In this case, I can see that I have dir A1 and 2 under that. I can go back out to the top of the file, and you can see I can see more of the fuller structure there. Yep. Okay. And then if I try to cd to an unknown directory, it'll give me an error, and then I just have to go to the correct one, and then I can see its contents. Okay. So I made directories, and technically those are getting written to the file as you make them, but let's try to actually write an object to the file and within the directories. So I open a file for writing, and just so you know, this recreate option means I'm going to be able to write to this file, and I overwrite any previous files if they exist. And if they don't exist, I make a new one. So I write to the top of the file by just saying, after I first open it, I'm within the directory being the top level of that file. And then I make some object and I say, write, and then it writes to the top of the file. And then I make a new directory, I cd into that directory, and then I say, write with some other name, even on the same object, and it copies that and puts it in the directory as well. And you can see after we open it and close it and then open it in a new session, we can see the structure I've created just like that, with the first name at the top of the file and then the second name under the next directory down. Okay. Are there any questions on T files or T directories? Okay, cool. So next, we can work with histograms. So this is to actually start to do data analysis and visualization. So several classes exist, TH1, 2, and 3. There's also, at least there used to be a THN, but I don't know if it's not really widely used. But histograms are intended to hold bin data in some number of dimensions. So let's say I have some set of scattering events, and I have some particle coming in with initial momentum p0, it strikes some target, and then that particle scatters off into some other direction given by some angle, and its momentum magnitude p1. And I can choose any of those and then have a continuous distribution with individual occurrences that I want to then bin into some histogram for statistical analysis in a bin way. And I can define some bin edges, and then I can say, okay, count the number of times that an occurrence happens within that given range, and then I make the associated the according number of entries in that bin within the histogram. And just to note, doing this way integrates over P1 cosine theta if I'm just looking at P0, right? Okay. So, I could do other things too. If I wanted to do in a different dimension, I could say have project this into some other dimension, make other bin edges in that dimension as well, and do the same thing. And that's what TH2 and 3 for the next step up complexity. That's what those are for. Now TH1 is the actual base class of all those histograms and sort of things that expand upon those. This is from the root documentation. This shows TH1 here and the different set of, or types of TH1, or the actual concrete classes of TH1, and then a TH2, its concrete classes, and then a TH3 and its concrete classes. So these are all sort of in the style of TH1 followed by some letter, and this indicates the type or the precision of data that would be sort of stored within that within the histogram itself. So I guess this is probably the bin edges, and also the counts. It will be stored as a specific type or precision. So is anybody confused on that part? Because I just realized that might be a little more advanced in terms of computer science than maybe somebody just diving into this. So it'll be only one data type per histogram, but when you fill it, or when you add an entry to the histogram, it'll do some conversion, right? So you can give it an integer. Let's say that you have a TH1D, and you want to give it, so that's a double precision floating point. And let's say you give it some integer, it'll convert that to a double, right? No problem. Okay.
So people should be memory aware.
Yeah, people should be memory aware, right? So if you, I guess, disregarding any sort of extra overhead that might be there, a TH1D will be about twice as big as a TH1F with the same number of bins and the same number of bits, right? Because they're twice the precision, or twice the number of bits within that number, representing that number. So most commonly you'll just come across TH1Ds, TH1Fs. I guess things other than that are if you have really long axes or a really small number of events, I guess. I don't know. I usually only see one, Ds and Fs for these, but just that being double and single floating point precision. Okay. And then, right, so yes, okay. There's some extra stuff here that I don't really get into. I kind of touched on no, actually, no, I don't. I don't really get into other things here, but they just inherit from these different histogram classes. Okay. Right, so when you actually work with these, you use those concrete classes, so like TH1D and TH2F. And like I said, you only ever really see double and floating point precision. And kind of going off what I said earlier, the TH1 class reference itself holds most of the relevant documentation, even for those higher dimension histograms. So they're sort of just additional abstractions on that TH1 concept. So you can really just go to the TH1 class reference for most of that relevant documentation. Okay, so let's take a look at how we want to work with TH1D. And let's look at just the most commonly used constructor, which is for equal width bins. So let's say I'm interested in some data in some set of units between 0 and 10, and I want to look sort of in bins of size 2, right, width 2. And those are all going to be the same size. You could just give it the name of the histogram that you want it to be named. You can give it some title if you want. You could just give it an empty string too, if you want to choose that title later or go untitled. You give it the number of bins that you want, in this case 5, 1, 2, 3, 4, 5. And you give it the edges of that axis. And then it creates that. That bin width, so some things happen under the hood, like it determines the bin width, which is just the upper minus lower divided by the number of bins. So that gives you 2. You can also do it with variable bin widths. And the way you do this is slightly different. Let's say I want to have my bins with that first bin be a width 1, the next one be a width 2, the next one a 3, and 4 for the final one. I can make some vector. Really, it's just some set of, contiguous set of memory holding some bin edges. And then I can provide that, provide the sort of, sorry, let me back. You provide it with the name, the title like normal, you provide it with the number of bins that you want, in this case it's 4, and then you provide it with the bin edges, and it's typically 1 less than the number of edges. Sorry, the number of bins is 1 less than the number of edges, right? So you have, if you have 1 bin, you have 2 edges. If you have 3 bins, you have, sorry, 2 bins, you have 3 edges. If you can look at this, it makes sense. So what you do is you give it the pointer to the start of these series of bin edges. So it says, here's this location of memory, and you know that it's a specific, it's a specific width, and look for, n number of places after that to get the bins. So this is one indication where you have to be very careful with memory when working generally in C++, although it's gotten better in recent years, but definitely within Proof. And you can create those bin edges however you'd like. So I showed a vector where I've pointed to the first element. And you can also do things like C-style arrays. So this is just, static width of a series of doubles in memory. And you can just provide it, because this is a pointer itself, you can just provide that like this. You don't need to reference it. And you can also provide more C++ style arrays like standard array, like this, and you can give it basically the same thing like in vector. So yeah, you can choose however you want to do this. Okay, so that's constructing TH1Ds in kind of 2 different ways, but let's actually go to adding entries, and let's go back to that equal width histogram. So these entries are themselves added with the fill method, and they're sort of added sequentially. You can modify these sort of heights themselves after you do this, or before you do this, really, but I won't really touch on that. Okay, so what we do is we give it a double representing the entry's value, and then it returns the filled bin. So if I give it 0.5, that should be right here at this green line, the second green line, and it'll say, okay, I'm within this first bin. Same thing if it's 1. And then it makes some decision on where to put 2, because that's right on a bin. Well, you say it's 2, but really under the hood in the computer, there's going to be some floating point precision. Anyways, it'll have to make some decision on where that will actually fill. It probably has some internal decision making to say, always give it greater than or equal to the lower bin edge. Okay. So yeah, you can see I filled several sets of bins, and this is actually what it looks like after we draw this histogram. And you can see it looks, according to how I defined it, or how I filled it. And we can use this histogram for more than just drawing and visualization. We could look at the integral, so the sum of, by default, it's the sum of the bin contents, so just like the height of the bin. All of these added together. You could also do it with the width, and this is essentially the area under the histogram. So it takes the height and multiplies it by the width of the individual bins, and you can see it gives you 10, because they're bin with 2, and there's 5 entries, so 10. You can also look at the number of entries. So these are the number of times I've called the fill method. You can see it returns 5 times. Okay. And you can also look at the specific number of entries falling into a given bin. So you just say histogram get bin content, and then you give it the bin number. And I want to make a note that the normal bin numbering starts at 1. I don't say that here, but that's because there's actually an underflow and an overflow bin, and that underflow bin is 0. So let's say I give it, fill -1, it will go into the underflow bin. If I give it fill 11, it'll go in the overflow bin, which is just, n bins plus 1. Okay. So you could also fill it with weights. Like, let's say you're running some Monte Carlo and you want to say, I want to change my Monte Carlo with some weighting scheme. You can actually fill that with a set of weights, and you can see that, for example, this first one I fill in 0.5, just 1. Okay, so that's just this. The second one I fill at 2.5, and I give it a weight of 5, so it's sort of 5 times that size. And then the third one filled 10 times, or with a weight of 10, and you can see it's 10 times the size. Okay. So the bin contents correspond to the weights we use. That's good. We still have 3 entries, though, and the integral still corresponds to the sum of the bin contents. But there's a new method that I haven't talked about yet called effective entries that that shows some weird number. And what does that actually mean? Well, we can see that from this nice root forum post, which is another useful tool that you should deploy. Go to a lot of times people have questions. You can just go to the root forums and look and get replies straight from the horse's mouth or right from the devs themselves. And they tell you that the effective entries returns the square of the sum of the weights divided by the sum of the weights squared. So why do we need this? And this is because those individual weights need to be book kept because the histograms no longer obey Poisson statistics, right? So we actually care what the individual weights are, and it does internal bookkeeping to determine what the size of those error bars are within our histograms. Okay. And to hammer that home, yeah, the square root of n or Poisson statistics error bars, that's no longer implied. So yeah, the forum is a nice tool if you ever get stuck on something. Look there, see if there is previous questions. You can also ask a question yourself, and people are mostly happy to answer for you. Okay. So like I showed earlier, and this is just sort of hammer on the point about the weights or the errors. You can also look at the bin error itself. Just like looking at the bin content, you just give bin error with the bin in question, and it gives you the size of the error bar. And this is going to be immensely useful during analysis or presenting results or whatever. Okay, so here's a couple different things like miscellanea that you could use with histograms. You can manipulate them, and you can do some arithmetic with them. For example, you could tell it to scale like a factor of 2 or a factor of whatever. And you can see it takes, this is back on the normal histogram, the unweighted histogram. You can see it takes the entries and just doubles them as I find it. You can see it also changes the size of the errors because, again, we're no longer using Poisson statistics. You can also do arithmetic with them. So you can take some histogram. In this case, this is the normal, unscaled, unweighted histogram. And I have some other histogram that I've created elsewhere. And I could say, okay, add it onto this histogram. I should have named these differently. So take histogram 2 and add it onto histogram A. And you can see histogram A changes accordingly. So the actual contents will be changed. One thing to note is that you actually have to provide the pointer to the second histogram. It's just funny root stuff. So they gotta get used to. Okay. And you can do more complicated things too. So this could be useful if you are, you have some, this could be useful if you want to sort of essentially broadcast some arithmetic over, you have the axes of your histograms. You can scale this by -1, so you invert it, or rather, you scale it by -1. And then add it to the initial histogram. So you're subtracting in this case. There's no specific subtract method. That's why this is needed. And you can see it changes the results accordingly. You can also multiply and divide histograms by each other. So taking this first histogram and then multiplying it by this shape, you can see, okay, things start to follow things change accordingly. You can divide it as well, and again, it changes its shape. So yeah, there's lots of different things you can do with histograms. When you're doing analyses, you don't have to loop over the bins themselves. You can start to use them with each other to get results. Okay. So that's working in one dimension. Is there any questions on that before I go on to higher dimensions? Okay, it's pretty kind of simple stuff. Okay, so working with 2 dimensions, making a TH2D is very similar to a TH1D. You just add a couple more bins, or a couple more things to describe the second axis. And here I just have equal binding. Unequal binding kind of gets a little wonky, so like to describe really. So I point you to the class ref. Go look at that if you're interested in these unequal bindings. But yep, you just do the same thing. You give it some name, some title if you want, and then something to describe the X bins, in this case, 10 bins from 0 to 8, and the Y bins, 20 bins from 0 to 10. And just to describe, show what this looks like, I've filled this 1,000 times, some Gaussians in each dimension. So I've given the X value to this first number and the Y value to the second argument rather. And then I draw that here. Okay. And getting the bin content, well, when you draw this, the bin content can be shown by the color of the bin and then the number on the z-axis or the color bar. Note that if you want to have this actual color bar here, you have to give it call z in the argument when you draw. Okay. I also make a note that g-style setOpstat0 gets rid of this sort of annoying and obscuring text box that you can see at the top right here. So that could be nice for when you're presenting results. Okay, you can also do arithmetic and manipulation just like we did with TH1Ds, but basically it's the same thing, just abstract it to another dimension. So I'll skip that for now, and then we'll look at several ways that we can view TH2 info. So you can just look at the distribution like this, but you can also project the data along it, onto an axis. So I say along an axis, but really I should say onto an axis. So let's say I want to look, what is this distribution like only in Y? Like integrate over all of X and show me what this looks like in Y, or X, whatever you want to look at. You just provide it with this projection X command. It returns a TH1D pointer, and then you can just draw that. And this is what that looks like. The default projection is all bins, but you could say, okay, I just want to look at bins 3 and 4 integrated along X and projected onto the Y-axis. And so you have to give the name, some name representing that TH1D, and then the projection, or the bins that you want to integrate up to and including. And this is what that looks like. Yeah, so this shows some slice in along X projected onto Y, 2 bins in this case. And here, I provide it with the same number. That's just 1 bin, so it's just going to be this single. Okay, I show 2 bins here, but it's really going to be one. No, sorry, I confused myself. Right, sorry. So there's, yeah, this should really be 1 bin here that is integrated along onto Y. Why did I do it this way? Sorry, this is confusing, and I drew these rectangles wrong. My apologies. Yeah, imagine that these rectangles are flipped. My apologies with that. Okay, I'll go fix that after the class. Sorry about that. So what it does is it takes, really what it would do is take the 3rd bin in Y, the 3rd and 4th bin in Y, and project that onto the X-axis, rather than what I've shown here, which is kind of the opposite. My apologies for that. Okay, same thing here, just rotate that 90 degrees. And you can explore the class reference for other methods like profile X and Y. This is actually useful if you want to get sort of statistics bin by bin. So this actually shows the mean and the standard deviation of each bin projected onto some axis. Okay, There's also TH3s, which are just the next step up from TH2s. You give it a third set of numbers representing the bins in the Z dimension. And then when you fill, you just give it another number to place, to find where to place. And when you draw, it looks kind of crazy and hard to sort of understand what's going on. So we can do those projections that we did previously to get it into 2D or even into 1D. So we can say project from 3D onto the Z-axis, so that's this one here, or onto the Y-axis or on the X-axis. And it integrates over the other two sort of implied dimensions when projecting. We can also integrate over, we can also say project onto the X and Y plane, and it will integrate over, in this case, the Z, and give you some two-dimensional distribution. And then the different, these are the different projections as well. Okay, so that's sort of a run through of everything related to histograms. Are there any questions on that? No? Okay, cool. So another commonly used set of objects are T-graphs and their derived classes. And these are nice to store and view discrete and ordered sets of data. So like individual data results or data points, like if you want to present some analysis results, T-graphs, and another one later on is actually more useful for that. It's also nice if you want to interpolate between them. So T-spline is another way to do that. And actually T-graph uses T-spline to do the can use T-spline to do the interpolation, but I don't cover that in this talk. So yeah, if you want to do, look at your data for this, that's what T-graph is for. Did I mess this up? No, okay. So, sorry, I'm not highlighting these much here. Okay, so in order to make a T-graph, you have to provide a set of X and Y values. If you've worked with matplotlib or pyplot, it's essentially the same thing. You give it the points in X ordered and the points in Y, and then in order, those are made into XY pairs and then stored within that T-graph. You provide it with the size of the number of points that you're interested in, and then, just like earlier, some pointers to the start of each of those representations of that data, and then it makes the T-graph. And then when you draw it, there are several options that you can give it, and sort of most important is this A option when you're drawing your first graph. You have to provide this. It says, actually draw these axes, and then I'll plot my graph onto that. If you give it C, that tells it to make this curve here and connect between those points. And then if you give it this asterisk, that says draw an asterisk at each of those points. You can give it P, that gives you like a marker or a point, I guess. Anyways, after this, what I'll do is I'll upload some additional places where you can look at how to draw both TH1s and histograms in general, and also graphs. Okay, you can also use them for interpolating between the points. So if you want to represent some PDF in this way, or a probability distribution function, or some weighting scheme, you can use this eval method to interpolate between these points. And the default is linear interpolation. So I take from point 1 to point 2, project a line. I evaluate at some point X, in this case 1.5, find where that crosses that interpolation, and that's the value that I get back. You can do more fancy things like a spline, which is what I mentioned earlier, which is just some other way to interpolate in a more smooth fashion between these points. So for whatever use cases you might need, you can choose accordingly. So yeah, see the class reference for those options. Okay, so there's also tgraph 2D, which is a similar class, but just for two-dimensional data. And that constructor takes the same thing, number of points. In this case, the X values of those points, the Y values of those points, and then just the z values. And in this case, I've just made some example where the z values are just x times y. So I've made, this is a bit messy, I'll try to explain this. I have some set of points that I'm interested in, 0 through 5. I iterate over those base points, essentially in a nested fashion. X gets the first point, Y gets the second point, and then Z gets those two multiplied together. And then I just provide that to my constructor, and it gives me an object back that I can then work with. And I can draw with this specific option, and that gives you this sort of nice interpolated view of this. Okay. So yeah, there's lots of different ways that you can actually visualize this. Again, look at the class reference. So this is just one option if you want to represent your data in this way. There's also T-graph errors, which is useful if you want to represent your points with error bars. In both, in the X and Y axis. If you don't care about the error bars in either of those axes, you can just provide it with zeros for those errors. But you just provide it with the same thing, the number of points, in this case 3, the X and the Y values, and then the error bars with their widths, so one-sided width in X and then Y for each of these. So sorry I don't have the code here. Something was wrong with my root installation, so I can show you this, but yeah, I don't have the screenshot. But it's essentially the same thing. You give it vectors, or rather points of memory that represent the start of a array of values that it will use for either the values or the errors themselves. Okay. There's also more complicated versions of T-graph errors called T-graph asim or asymmetric errors. These are for things if you don't want these error bars to be the same on either side of the point. So, like, let's say you want to set a limit, you can use asim errors rather than like some, Gaussian-looking error points. Okay, so that's TH histograms and graphs, and now we'll go on to sort of really one of the more powerful objects in Root called the T-tree. Okay, so T-trees represent what's called columnar data, which is a set of, it's kind of like a spreadsheet with some sort of efficient assumptions made about how you want to actually access the data. It's a set of entries, also called events pretty often, each of which has one or more variables or columns, also called branches, that are associated with it. And within Root, any C++ type can be stored in a column, and Root just needs to know how to, what the structure of that class is. So for Dune's current processing framework, we use lots of complicated C++ classes that are actually stored within files. We just have to give Root the instructions on how those are structured. But certain things like simple types like ints or doubles or standard containers like vectors, those are already in Root's library of things. So you don't need to do it for that. Anyways, I'm going on that point too much. Yeah, any C++ type can be stored in those columns. Okay. So a column in Root is called a T-branch, and when analyzing data from a T-tree, one of the benefits of columnar data is that you can process data, load it into memory, grab it from storage, with only subsets of those branches at a time. And this makes for efficient input and output and makes processing simpler for you. You don't have to sift through all of the data and find the specific branches that you want. You can say, I just want these branches, and then yeah, and then look at that. Now each of these branches can have one or more T leaves. These are specific members of the class chosen to be saved. So I can make like a struct. Do I show that? Okay, I might show that later. You make a struct, and then that struct has several members. And you can tell it, save this member, and you need to give it some specific information about what that member is. Honestly, I haven't used that too much, and I haven't seen it used too much. People just make classes instead, and then save those after they give Root the instructions of what they look like. So you might come across this, but you might not. Okay. So let's look at how you actually make a T-tree and then add branches to them. Okay, so I make some file that I will use for this example, and then I start to make a T tree. So you just give it the name of the okay, I called my tree not root, my bad. Okay, so you give the name of that tree, and then you give it some title. And then now it's in memory, and you can start to work with it. And a branch, like you can start to add branches to it. And then most simply, you just need to give it the name of the branch that you want to create, and then some pointer to some object representing, representing something that root will then reference when it's adding entries to the tree. If you just do it this way, it will follow the type of the branch will follow the type of the object that it's pointing to. So in this case, you can see, all right, I have an int, and you can see it says /i here represents that it's an integer. Okay. And there are, after you start to add branches, or if you get a file and you don't know the structure of some tree, there are several ways that you can look at that and start to get some information about the tree, so you can start to work with it. So for example, there's show, which just gives you the list of branches. In this case, it's just one. And then there's also get list of branches, which returns a T list of T branches. And if you print that, it starts to give you more in-depth information. So like I said, any concerns about I/O, like that you usually don't need to care about. Like this is how it's stored in memory and whatever. Most of the time, you just need to know the branch and then the type. Okay, and we can continue to add more branches and see the structure of our tree grow. So I've already added branch A. Let's see, okay. Now I have a new branch that I'm just going to call double branch B to represent that it's a double. And I'm going to point to a double that I'll use to store fetch information from later. You can see when I show or when I print the list of branches, you can see it starts to add show more information representing the stuff that we've added. But you can see if I use this method get entries on this tree, no entries are there. So we don't have actually data in our tree. So this is where we start to fill things. If we do this just now, when you call fill, you add an entry to the tree, and the branch values for that entry correspond to whatever the value of those objects are that you've already pointed to. So I've just initialized these first two things with 0 here and here, and then I call fill, and you can see after I use this method that I'll go into later, scan, you can see that the values of these branches within my tree are 0. And you can also see that we've added an entry here, and that's represented by this get entries method. Okay, so let's actually try to set these to something. And we can set them and then fill them, and then it fetches the value of those objects and puts it in the tree. And you can see that represented within the scan function here. They match accordingly, which is good. You can see we've also added another entry to our tree. Okay, so we can start to, sorry, you have a question?
I was just wondering about when you add an event to the tree. So you see branch A equals this, branch B is equal to that, and then once you put basically to use the fill method,
Yeah.
whatever those branch that is equal to will be assigned to new event. Is that correct?
Yeah, so, right. So, yes. The tree will sort of, make another entry in its memory, or in its like list of entries. And then for all the branches that you've added, like that you've created already, it'll take the method, sorry, it'll take the value and put it into the tree. That answer your question? Yes. Yeah. Right. Yeah, so that fill just does everything for you, basically. Okay. And so we can start to add more other types and more complicated objects too. So we can try a string, we can also try a vector, we can also try this struct which contains leaves. So this is the tea leaf thing that I mentioned earlier that I really haven't seen used, but I thought I might include this anyways. It was actually kind of instructive. So I might actually start to use this more. But let's see what this looks like. So I have several sets of objects here. I have an integer, a double, we've seen that before, integer. I have a Boolean, I have a string, I have this struct, and I have a vector. And really things are pretty straightforward. You just give it the name that you want it, and then you point to that object. The one that's different is this branch containing leaves. So this is nice if you want to just kind of give it, like, let's say I want to represent some like subset of data, and quickly and easily put that into my tree. You can create a struct that holds that data, and then you can make a branch, and information about that struct and the sort of data to extract from it. For example, the name of the individual objects or the members, and then their types. So a long int, or sorry, unsigned long int, a double precision floating point, just a normal int that's specified by this character here. And it will take those, and then it will store them accordingly. So this is actually kind of useful. I haven't seen it used as much, but I might start to use this now. Okay, this is really important though. One thing to know, this is really important to, you have to specify the name of the members of that struct and the type, and you have to get that correct. Because if you don't, weird things in memory can happen. So it uses that to say, I know the next n number of bits is represented by, or should be used for setting the value of this given leaf. And if you use the wrong one, it's going to give you the wrong value. So I actually kind of learned that the hard way, but it's really important to get that correct. I think it's probably one of the reasons why it's not used very often. Okay. All right, now let's look at we started to add information to our tree. Let's look at how we can actually look at that. And I made a toy Monte Carlo script for the example, and I think that's in the GitHub for the workshop. If not, I'll add that. Okay, so we're gonna do a couple things. We're gonna scan, which we've shown already a little bit. I'll go more in depth in what's going on there. We're gonna look at drawing from the tree, and then also look at analyzing things event by event. Okay, so for scanning, this is really nice to use. If you want to just check things and try to delve a little deeper into some fine-grained information. And you can see sort of this is what it looks like after we use the script that I made and ran. You can see a bunch of different values for this thing that looks like momentum. You can see these strings that I've added here, and then you can look at the tea leaves. So this is saying, all right, so stuff is cut off. That's one of the cons of using this. But you can see each of these is hidden, but it will be mybranch.r1, .r2, and so on. Yeah, and it shows the row being the entry number, and then also shows the name of the branch being shown, and not all are shown. But you could look at a specific row. Sorry, I got to be careful about the sort of overloaded terms. You can look at a specific entry, and I can look at a specific column and see, okay, for that event or that entry, this is the value of this branch. Yeah. We can cut down on the information being shown if we use this separated list of branch names, and really it's an expression. So you can do math within it, and you can say, multiply branch A by branch B, and then things will come out accordingly. And you can do that using this colon-separated list of branch names, or really expressions. And this shows, like, for example, the momentum of some particle, whether that particle interacted, and then if it did interact, the type of interaction that it was. And you can even start to filter things by giving it some conditional expression in that second argument. So, for example, I only want to look at the entries that have interacted. And you can verify for yourself, but the entry numbers here, the entry numbers here correspond to the entry numbers where this is true, right? So, like I said, interacted is a Boolean itself, so this is a really simple case. And you can start to make things more complicated because it's an expression that gets evaluated. So you could say, I want to look at events where there was an interaction and the number of products coming out of the interaction is above 5. And so you can see all of these are above 5. These are all 1 because they interacted. Okay, so that starts to make sense. Yeah, okay, I also note that, I kind of mentioned this earlier, those columns are themselves expressions, so you can make complicated representations of your data, semi-complicated representations of your data here, and get some more information out too. You can also compare strings, and there's one hiccup that you need to account for, which is just that because in C++ you can only give, double quotation marks to denote strings. You have to escape this string here, the quotation marks around the string with a backslash. Okay, but this shows that you can still filter based off of string content. You can see now all of these are elastic interactions as according to inelastic interactions. Okay, now we can also look at vectors too. So one of our branches was a vector, and we can see its structure when we're scanning too, as long as we start to actually look at it. This product R's is that vector I'm talking about. So you can see that there is a new column in this display that shows the instance. Essentially, that's the number of times this entry has appeared in this scan because some vector has had another entry within that vector itself. Okay, so there's certain things you gotta get used to. So values are duplicated, like single entry values are duplicated over and over again according to the size of that vector. One thing you gotta get used to. It's kind of nice to make things easier to compare to. But you can see the actual set of values within our vector here. You can also see vectors are empty when there's no interaction because of how I made the script. But when they're empty in data, they're empty in the display. Okay, that makes sense. Okay, this is kind of getting more and more complex. You can also filter based off of the size of the vector and look at a given instance of the vector itself. So for looking at the size, you need a special syntax. You have to prepend it with this @ symbol, and that allows you to use this method here. But you can use that to look at information about that vector. And you can also look at use that within filtering to say, okay, give me entries where the number of entries within that vector is above 5. And I want to look at the fifth instance within that vector there. Okay, so you can do a lot with scanning, and it's nice again if you want to look at like maybe specific events and find great detail, but it only gets you so far, and that's where drawing comes in. And the syntax is very similar. You provide some expression that you want to represent your data with, and then a set of an optional set of filters or set of filters that you want to, or optional set of expressions that you want to filter your data based off of. Okay, so I can take that tree, and then I can draw the momentum distribution. Okay, it's a nice looking Gaussian. And then since that's an expression, I can manipulate that. So I can transform our data in some way. Like I can make it a normal distribution, or normalize the distribution to 1. So I will subtract the central value from it and then divide by its width, which again you can see up here. And you can see, okay, it's centered at 0 and it's got a width of 1 now. Cool. But you can also do more complicated things. So the C++ standard namespace functions are available too. So I can look at the exponential value. I can use the exponential function and look at the value of that. You can see that changes too. There's also one thing I gotta make sure I add is there's also other there's like a library within root called tmath that gives you other things like the value of pi or like cosine and sine, although those are also standard functions. But yeah, I'll show you how to do that too after I edit the slides too. But you can get creative with this. So if you find a C++ standard namespace function that you want to look at, try it. Okay. Sometimes it's useful to bin our data. to make it easier to view or understand. So if I just draw the number of products, you can see, okay, I can see lots of information. I can see sometimes you get out to 100 products. I can see this big spike here, and I can see the general shape, but what if I want to look at things in a different view? Well, I can provide this binning here, and it's basically the same syntax as when you create your histogram. And so you just give it some expression, in this case, just the number of products, and then you give it this, you give it like a pipe, right? Like 2 greater than signs, and then the number of bins, the low end of the axis, and the high end of the axis. So usual TH1D constructor. And now it looks like this. So we've gone through all the entries in our tree, and then I've taken the value of the entry, the end product's value of the entry, and I've placed it into my histogram. And kind of the same thing earlier, I said that there's underflow and overflow bins. Those are also accounted for here. Okay. Now, that only gets us so far. What if we want to start to actually use that histogram for some analysis? We can actually put that into memory by giving it some histogram name, in this case, products hist. And within the root prompt, that could be immediately accessed via that name. And so you can see I reference that here, and then I can start to look at information about it. So the number of bins and the integral. You can also sort of do this the other way around, right? So if you make a histogram first, then I instantiate that in memory, and then I call it products hist, and then I draw essentially into it, then you can see that it fills that histogram. Sorry, you can see that it places entries into that histogram, and yeah. And note, you can also get the histogram from this singleton known as G directory. So this is the sort of current working directory that you're under. And if that object is there in memory and it's managed by root, you can see its name, you can grab it by its name and then start to work with it in the same way. Okay. We can also filter that data just like we did when we scanned. So we can say, what are the number of products in this shape of histogram when there was no interaction within that entry, and you can see it returns the number of entries passing that filter, and then draws that expression. Here, all these entries are at 0 because just of how my script works. I dictated that there's no interaction products. Okay. And I can look at the ones where there is some interaction. I can change the binning as well. And you can see the shape of that changes pretty obviously. And yeah, now we can start to see some structure of what was going on within that little toy Monte Carlo that I was doing. Okay. And then we can draw 2D 2D histograms or distributions just as easily. If I draw sort of end products versus momentum and give it this call Z argument, this tells me to give you this color bar, you can see this is the distribution it draws. If you give it no argument here, it just draws each of the individual points on some distribution here. Okay. I make note that the syntax is y versus x, so end products is on the y-axis, and x-axis is on, the momentum is on the x-axis. One confusing point is that this is different from how you'll define the binning, right? Or the order of this is a little different. So here you're saying, I want to look at my products as a function or versus my momentum, but when you make your 2D histogram that you want to draw into, it's your x-axis first and then your y-axis. So this is because this is the constructor for some histogram, but this is like how we would say I want to look at my number of products versus the momentum, or as a function of momentum. So it's a little tricky. It's just one thing you have to get used to. Okay. So if you're interested, you can try this in 3D. So add some other. I think I have that tree maybe within the GitHub. So you can try it in 3D. The syntax is similar. You just say, ooh, I think it's Z versus Y versus X. And then you have to give it X bins, Y bins, Z bins. Okay. But again, you can always look at the class reference. Okay. So that's scanning and drawing things. Now we can look at things event by event. And yeah, you can get a lot of analysis done by using the draw method, but if you want to start to do more structured, want to look at more structured branches or more complex analysis or transformations of your data, this event by event iterating is useful. Okay, like I mentioned earlier, the data is columnar, which means we can choose a subset of the branches that we want to actually look at. So let's look at these four: event number, momentum, interaction type, and then this product R's, or this vector of doubles that I made. Similar to when we made those branches, we just need to provide some location and memory that data will be sort of unpacked into. And then you need to know the branches. So we need to know the branch's name and the type. So we say set the address of this branch, and that branch being event number, set its address to this address that we've already created in memory. Yeah, and then it'll sort of pipe that data into there after we start to extract the data. And because this is, you have to get these things right, get list of branches print helps with this. You can look at, okay, whatever branch I want to look at, you look at its type. This is helpful for things like tea leaves or vectors, stuff like that. For vectors and other containers, we need to provide a pointer to the object. I'm trying to figure this out. I think it's because root needs to be able to dynamically allocate and deallocate memory, so you have to give it the address of a container rather than just the address at the start of the container, so that it can manipulate that container size and stuff. And if you try to give it just a straight up vector rather than a pointer to a vector, it will complain. Yeah. So give it the vector and it's all good. You also need this for strings because they actually behave like vectors, right? They're a variable sized set of characters that can grow and shrink in size, so you have to do the same thing there. And after setting these branch addresses, we see that the objects we created still have their initial values, right? This is because we've not actually said to the tree, look at this specific entry. We just said, here's the under the hood C++ stuff that you'll use to actually look at that information. So what we'll do is we'll say, okay, tree, get the entry at row 0, and then it sets the values of our objects that we've specified earlier. So we can look at that here. The momentum looks around 5. That's because it's a Gaussian, around 5. You can see the interaction type. Again, this is a string, so we have to dereference it, and then you can see it there. Same thing with the double vector there. Yeah, so it's pretty self-explanatory. But let's go to a more interesting event. So we can skip around the tree. We don't have to go in order. We could say go every n number of entries within the tree. So let's go from 0 to 5, and we can look at that here. And if you'd like, you can compare it to the scan and compare that these match up. So you can see the event number is 5, the momentum is some other number. There's actually some interesting interaction type. There are some values stored within that vector. Cool. So that shows up how to sort of set things up, and then the general analysis workflow will be like this. We have some T file that has information that we're interested in. We open that up, and we access the T tree that's stored within it. We make our objects where we'll read data into, and then we start to loop over those events or those entries. We get the entry, we process that information, okay, and then we go to the next entry. Now that processing can be really complex. It could be, writing things or filling histograms or, doing calculations with whatever value that we've unpacked from. And then after that loop is done, okay, now we decide what to do next. We can do more analysis on that collection of data. We can write that to a file, whatever. But this is the general sort of workflow. Okay, now I think I'm almost done here, yeah. And a look to the future, after giving you all this nice information about T-trees, there's a new beast coming down the line called RN-tuple. And Root is heavily pushing for everybody to use this. And it's a new columnar data format, and it's from what I looked at, it's basically the same, well, it is the basic same column and event style of access. The syntax is just slightly different. And it actually interfaces with another newer class called RDataFrame, which actually allows you to process data in a more data science-y way. So it's kind of similar to how you process some things in NumPy with like broadcast. I think it allows you to do like broadcast operations and things if you're familiar with that. But it essentially allows you to do like different filters and like transformations of your data in kind of a more, again, data science-y way. The benefits of this is that it's more efficient persistent storage sizes and I/O speeds. And from this example from Root showing some preliminary open data from Atlas, you can see that the size of the orange tuple compared to the tree representing the same data is about half. So that's pretty cool. So T-trees will still be around, but I do recommend that it's a good idea to start familiarizing yourself with this new format. And I say that as somebody who hasn't done that yet, but it's relatively new. I think only since Root, I don't know, 6.34, which is relatively recent, this has been available for everybody to use. Okay. So, anyways, I bring this up and I say in a bit of a joking way that okay, all the information about T-tree will be kind of overwritten. It's not exactly true. The same style of like information getting will remain. You can still do this sort of event loop, but you can do more cooler things with like data science kind of techniques. Okay, all right, so let's wrap up. Root's this big tool with a lot of use cases and functionality. So I can't cover it here, but the documentation is very good. So these class references that I've continually, multiple times I've recommended you look at, these exist for basically all of the classes that you'll encounter and that you'll use. In the forums and the community provide additional guidance and deeper explanations from the developers and computational science perspectives. So yeah, there's lots of information that I covered here. There's still lots of information to go into, but hopefully this gives you some a good baseline to start. So thanks guys.